Hi everyone, I'm Zhang from Rice University IC Lab. Today I'm going to present AutoMBA efficient and effective search over the joint space of networks, Bitwidths, and accelerators. First, I'm going to go over the background and motivation, then the proposed method, and then the evaluation results. So as we know, DNA accelerators are determined by three factors: network structure, network precision, and their accelerator architectures. However, individually optimizing these three factors can lead to suboptimal hardware efficiency and also the task accuracy. So that motivate us to joint search these three factors at the same time. However, the joint search is hindered by three challenges. The first one is the dilemma between the huge memory cost or the biased precision search when you optimize for the precision. And also the non-differentiable hardware accelerator search space. And finally, the chicken and egg problem between the optimal network choices and also the optimal accelerator choices, as we introduce later. To this end, we propose AutoMBA to enable joint search for networks, Bitwidths, and accelerators at the same time, and to solve the above three challenges. Extensive experiments validate the advantage of our proposed AutoMBA. The general formulation for AutoMBA can be very straightforward. So it has two types of loss: task loss and hardware cost loss. And our goal is to minimize the fused loss of these two. The question is how to sample and update the alpha, which is the network structure parameters, beta, the precision parameters, and phi, the hardware cost parameters. So first, we are going to focus on the precision parameters beta. So traditionally, it has like two strategies. The first one is activate all the precision choices during search. However, that will incur large GPU memory consumptions. The second choice is partially activate some precision choices during the search. However, that will bias towards some certain precisions, which is not ideal. As we can see from the left figure, when all the precision choices are activated, the GPU memory consumption basically exploded. The right table, the middle two rows, shows the partial activation of some precision choices during the search. All of them leads to a suboptimal accuracy, which is also non-ideal. To this end, we propose a strategy called heterogeneous sampling, which namely we use Soft Max when updating weights omega for the network choices. And we're going to use STE to save the memory when calculating the gradients. And to update the beta, which is the precision choices, we use hard Soft Max. So only one hard choice is going to be activated. So when we introduce additional network choices, no additional memory will be introduced. The second challenge is the non-differentiable accelerator design parameters, which are determined by the microarchitecture and data flow of the proposed hardware template. To solve that part, we use a strategy using hard Soft Max to sample each accelerator, so they are differentiable with respect to their corresponding accelerator parameters. And we also introduce penalty on the sample accelerator parameters through relaxation in a gradient manner. The third challenge is the chicken and egg problem between the optimal network choices and optimal accelerator choices. Basically, optimal network needs the operational-wise cost, which is determined by the optimal accelerator. However, optimal accelerator is also determined by the optimal network. So to break the loop, we introduced a strategy called single path forward and also multi-path backward. So basically, during forward path, we use hard Soft Max to sample the most likely network options to produce the optimal network as a approximation. And then use that to produce the hardware optimal accelerator and to produce the operational-wise hardware cost, which is going to be used as the input for the path backward. So the above basically solve the three challenges hinder AutoMBA. And then we're going to show some results. So firstly, AutoMBA consistently achieve better results against the SOTA hardware networks when they are accelerated by their optimal accelerators in terms of better accuracy and also higher FPS. AutoMBA also consistently achieves better win-win solution in terms of accuracy and FPS when compared with the co-exploration works. We also provide a snapshot of the search network and accelerator. So basically, the accelerator favors wide but shallow networks for better channel parallelism and a higher resource utilization. Also, earlier layers also prefer like feature-wise parallelism as the feature map is larger. So that basically summarizes the AutoMBA as a work to joint search for the networks, Bitwidths, and accelerators at the same time for higher accuracy, higher hardware efficiency, and a lower storage need. Thank you.